Today we're going to begin the next topic in calculus called derivatives. And these three concepts that we've got written on the right-hand side of the screen, I want you to begin thinking of these as meaning the same thing. If you hear the word derivative or read rate of change or see slope of the tangent line, they all mean the same thing. They all mean that we're going to take a derivative. So that's where we're headed with this, is learning how to find derivatives of different functions. Derivatives are related to slope that you've already learned about in algebra. This is the formula that you probably remember for finding the slope of a line. The slope is y2 minus y1 over x2 minus x1. And if you remember, we found this by finding 2 points that are on the line, and we would take the y coordinates and subtract them, take the x coordinates and subtract them, and divide, and we would call that the slope of the line. Well, that works very well when we're dealing with a line, but what do we mean when we're talking about something that's not a line, something that's a curve? Let's take a moment and look at this example on the next screen here. This blue that you see here is the function f of x equals x squared. So it's just a parabola. And what we're asking you to do is find the slope at a particular point. So let's say that we want to find the slope of the line, the slope of the tangent line at 1/2. Well, now what does that mean? That means we want to know that if we draw a line that's tangent to it, which would be just barely touching at that one point on the curve like this, if we were to draw a line like this, what would the slope of that line be? And that information tells us certain things about the graph. Well, we can't use the formula that we use with a line because we've only got 1 point. So what if we got out here, let's say we got out to this point right here, about 1.25. Now we've got 2 separate points here. Could we find the slope of those 2 lines? I'm sure we could. And if we look at this, I've got in the picture here, I've got it calculating that the slope of this line that you see right now is 1.72. But that's not the line we're looking for. What if we move C closer to it? What if we moved C closer to it? So let's say C was at the point 1. Well, now our slope is 1.5. Is that the line we're looking for? No, it's not. Well, maybe we want to choose a C that's over on the other side. Maybe we want to choose, what if we chose to use 0 over here? We got the slope there to be 0.5. So the slope here is 0.5. The slope here is 1.5. Would you think that the slope that we're actually looking for is somewhere between those two? Well, what can we do to get a better estimation of it? What if we moved C closer to the point A? Look, our slope moved down to 1.3. If we get closer even, we get to 1.14. As close as we can get, 1.18. And what if we go right on the other side of it? It's 0.93, 0.92. So it would appear that the slope is somewhere between 0.92 and 1.07. Wouldn't you agree? What number would be a good guess for that based on this point here? So I think we could conclude that the slope is about 1 in this example here. Well, but that's only at that particular point. What if we moved our point A here over here to -1? So now we're looking for the slope of this function, the slope of the tangent line here. Again, if we move our points closer, notice that we've got a slope of -1.48. We've got a slope of -1.91. If we move on just the other side, we get -2.07. So I think just if you were to write those numbers down, you would see that the slope looks like it's approaching the number -2 at this point. And we could go through that same process at any given point. Does any of this remind you of what we did with limits? It should, because if you think about it, what are we doing? We're taking this point and we're getting it closer and closer to the point that we're looking for. We're actually graphically taking a limit as we get closer and closer to the point A. So we're taking a limit here, and we're moving these 2 points closer and closer together, and by taking that a limit, we call that the derivative. So graphically, this is what's going on. If we actually look at it algebraically, here's the definition of the derivative. This is very scary looking, but understand that these two things mean the same thing. This thing up here and this thing down here are both meaning the same thing. If f is defined on an open interval containing a point C, and if the following limit exists, then the line passing through the point C, f of C, with a slope of m is the tangent line. So that's what we mean here. We're going to find the slope of the tangent line by using this limit here. Notice that this right here looks very familiar to some problems that we've done before when we didn't know what a derivative was. You were actually finding a derivative at that point. So this is our basic definition for what a limit is. This is one of those things that you will memorize and you need to be able to recognize. It's the limit as f of c plus delta x minus f of c over delta x as delta x goes to 0. If we can evaluate that, then the limit exists, and that limit is the derivative. These are different ways to write the derivative. By far, the most frequent way that you'll see it written is f and a tick mark x. This is read as f prime. Okay? So that's how you want to say it, f prime of x, or the derivative of x. This is also a common way to see it written. This would be read as the derivative of y with respect to x, or dy dx is how you'll hear me say it. Y prime means the same thing. And this would mean the derivative of this function with respect to x. All of these are just different ways of writing it. You just need to recognize that. The ones that are most common are f prime, dy dx, and y prime. Those are the three that you'll see the most often. So be sure that you can recognize them as the limit. So we're going to move on now, and the best way to learn to do this is to take some problems and actually work through these problems. So let's move on to the next slide. Let's move on to the next slide and find the slope of the graph at the point 2, 1. Well, I'm taking over this is the equation of what the derivative is. So we're going to take this function that we've got written up here, and we're going to evaluate it, the limit, with this function. So how are we going to write that? The way that you write it is very important. Be sure that you write it out properly. Don't leave the limit sign, the symbolism off, because it will affect your grade. And we want to find the f of x plus delta x. That means we're putting this number, x plus delta x, in place of x up here. So I'm going to write out 3x plus delta x minus 5. Then the subtraction sign that I've got right here. F of x just means this symbol again, since there's a minus sign, so be sure we write it out in parentheses, over delta x. Now notice I'm not using the point out here yet. We'll evaluate that in a moment. So for right now, I want you to look at this limit. Should be very similar to problems we've done before. And let's see if we can evaluate it. If we distribute, we get 3x plus 3 delta x minus 5 minus 3x plus 5 all over delta x. If we evaluate that, the 3x's will cancel out. This 3x and this 3x will cancel out. Negative 5 and positive 5 will cancel out. So we're left with the limit as delta x approaches 0, 3 delta x over delta x. Still can't evaluate, but we can do some more simplification. The delta x's will cancel out, and we're left with an answer of 3. So then we've evaluated this, and we've come up with a new function. We've come up with f prime of x equals the number 3, because that's what we got out. This said to find the slope at the point 2, 0. Well, if you remember from before, this is an x number. So to find the slope of that at that particular point simply means we're going to find f prime at 2. How do we evaluate that? We plug 2 in for x over here in our rule. We don't have any x's, so the slope is 3. So this is the procedure that we will go through to find the derivative. And if you think about it, remember that derivative is slope. Remember that this is a line if we graph it. And you could tell before you walked into this class that the slope of this line was 3, so you'd expect the derivative to be a constant number 3. So if you've got a linear function like this, you would expect it to be just the number in front of it here. And that's what we got out.